So in the last lecture, we have seen that how Liouville von Neumann equation describes the time evolution of density operator, which is basically given by d sigma t divided by dt is equal to minus I, commutator between the Hamiltonian and sigma t, right? And the solution to this equation was given by sigma t e minus I h t sigma 0 e I h t and this applies only when Hamiltonian is time independent, right? And we also saw how this solution can be further simplified to using BCH formula, and a modified form of BCH formula I should say, sigma 0 minus IT divided by 1 factorial h sigma 0 commutator plus IT square by 2 factorial double commutator plus IT cube by 3 factorial and triple commutator now, and so on, right? So far this is for time if Hamiltonian is time independent. Let us now try to see case 2 where Hamiltonian is time dependent. How to solve this equation when Hamiltonian is time dependent. So let us first see what you actually mean by we have been saying Hamiltonian is time dependent and time independent. What do you actually mean by that? So as we have learned that NMR experiment can be basically described in terms of a sequence of pulses and delays, right? So you have a pulse delay, and different combination of different type of RF pulses and different type of delays, right? So you have a delay here and this is a RF pulse. So during delays, if one considers, let's say there is no spin-spin interaction or no spin-spin coupling happening and only chemical shift Hamiltonian is being applied, then the Hamiltonian is time independent, right? So H is time independent, let us say, if a simple case of no spin-spin coupling is considered. So this is during delay if no spin-spin interaction so effectively no spin lattice interaction is considered here. So nuclear spin to electron spin interaction is also not considered, and all we are considering is just the precision about the static B0 field where there is no time dependence, right? So in such a case Hamiltonian is time independent and the above solution can be applied. Now let us now see when RF pulse is applied, for example. So during an RF pulse, during here RF pulse or during coupling evolutions, Hamiltonian is time dependent, and thus this above solution which we just discussed cannot be applied to the Liouville von Neumann equation, and thus we need to look for an alternative way to find the solution, right? So now how do we go for that? Let us say that if we can convert Hamiltonian using some trick from time dependent to time independent. Okay, let us say that if we are able to do this conversion, that uh, s- by doing some mathematical trick, if we are able to convert Hamiltonian from time dependent to time independent, we should be able to apply the same solution to Liouville von Neumann equation, right? So how do you convert Hamiltonian from time dependent to time independent? That is a question now. So if you remember the block equation discussion, where we were discussing the going into rotating frame of reference. So essentially what we were doing is we were by applying a transmitter frequency, we were going into rotating frame, and thereby we were actually removing the time dependence there, right? So a quantum mechanical treatment, a similar or equivalent quantum mechanical treatment in for rotating frame transformation is, so rotating frame transformation in quantum mechanical treatment is done by something called as similarity transformation. So similarity transformation is nothing but taking a matrix, a given matrix, to an alternative space, uh, which is, so again the two matrices are, so let me just describe what I mean. So let us say that if this is my density operator, and if I multiply it by U and U inverse, where the U are unitary matrices and U inverse, then this sigma is converted into sigma R, okay, where this is density operator or density matrix in rotating frame, let's say, and this is a unitary matrix. So here sigma and sigma R are called as similar matrices. Okay, so all we are doing is we are finding a matrix, unitary matrix, such that if we multiply on both sides, one side with U and another side with U inverse to density operator, what we are getting is a transformed density operator, which has such that the Hamiltonian now is time independent. Okay, so if we do this transformation, Hamiltonian becomes time independent, and we will see that. So that means this is a rotating frame transformation equivalent of block equation. What we have done in block equation treatment of NMR uh, uh, is similar to similarity transformation done in quantum mechanical treatment. Okay, so what is a U matrix? It's a unitary operator. By unitary operator I mean that U inverse is equal to U adjoint, right? What is an adjoint? Adjoint is, this is this is basically a transpose and complex conjugate, right? So this we should all know what is adjoint, and U inverse is given by the relation U inverse is equal to identity, right? Identity matrix of a given order. So this is how inverse is related. So here we are saying by unitary that U inverse is nothing but U adjoint. Okay, so let us now see the time derivative of the transformed density operator. Okay, so now if we want to calculate the time derivative of transformed density operator. Let us try to do that and see if we can actually get to the similar form as the Liouville von Neumann equation, original equation. Okay, so this will be given by d u sigma u inverse by dt, and now I can expand this. So all of these are time dependent, so I will write du by dt and sigma u inverse plus u d sigma by dt u inverse plus u sigma du inverse by dt, right? Okay, now what I will do is I will just multiply here by u inverse. I will insert u inverse here, so you will see that du by dt. So I can multiply anything by 1. Identity is basically like 1 multiplying by 1. So what I will do is I will insert u inverse u here, sigma u inverse plus u d sigma by dt u inverse plus u sigma, and here I will insert u inverse u d u inverse by dt, right? So this is also equal to E and this is also equal to E, right? Both of these are equal to E, so I can do this multiplication. Okay, now let's see what I get over here. So then my d sigma r by dt becomes, so it's a simple calculation, nothing fancy about it, du by dt and u inverse sigma r, right? So I can write this part as sigma r. Similarly, this part will be written as sigma r here, right? Okay. Plus I u, and I had d sigma by dt over here, so d sigma by dt u inverse plus this will now be sigma r u du inverse by dt, right? Okay, now this can be written as so this is the original operator, time evolution of the original density operator. So now I will write this as, there was no I over here, sorry, right? So I will write this as I sigma h, right? This can be written as I sigma h. So that means now what I've got is du by dt u inverse sigma r, I'll bring up this one here, sigma r u du inverse by dt plus I u, commutator between sigma and h, and then u inverse, right? This is fairly simple. Now also let us simplify these two. So if you remember that we had just mentioned that u inverse can be written as E, and if I now take time differential of this, so I will get u du inverse divided by dt plus du dt u inverse is equal to 0. This side is constant, so derivative will be 0, and that means one of them can be replaced with the other term with a negative sign. So that means now I can write over here minus u du inverse divided by dt. So this term is basically this term. So I'm writing this term is equal to negative of that, plus then I have sigma r plus sigma r u du inverse by dt, and the third term, which is plus I u sigma h u inverse, right? So it's a simple mathematics, nothing fancy. So then if you notice, this one is nothing but the commutator between sigma r and u du inverse dt. So I can always write this as sigma r u du inverse by dt commutator, and the other term is I'll take u's inside now, so u sigma u inverse u h u inverse, right? All I've done is taken the u inverse inside the commutator. Now this term becomes equal to sigma r, so that means I can write this as sigma r u du inverse by dt plus I sigma r u h u inverse, right? Now I can write this as I can put minus I square here so that I can take I common. Then I'm left with I, and then I can take sigma r and bring this in the same commutator. So what I've got is sigma r u h u inverse minus I, which is coming from here. So if I've taken I out, I'm left with minus I. So minus I can take inside here. So and then u du inverse by dt, right? So this is a simple enough to understand. Now this equation looks very similar to original Liouville-von Neumann equation, where I can say that this is sigma r h prime d sigma r by dt, right? So where h prime is nothing but u h u inverse minus I u du inverse by dt. Now if I have a unitary operator which can convert, which can take h to time from time dependent to time independent, here h is time dependent and this h is time independent. Then I have the same Liouville-von equation where I can apply the exact same formula, exact same solution to this equation, which we have seen earlier, right? Okay, so now how do we find out u? That is the question, right? So what will be the functional form of this unitary operator u? So let us first consider a simple case of spin half system, isolated spin. So why isolated? Because now we are not considering any spin-spin coupling, so any complex interactions. So we are considering a simple spin half system, and consider an RF pulse being applied, because we know that RF pulse is a time dependent Hamiltonian. We will see how it is time dependent. RF pulse is being applied on this. Okay, so now what will be the form of h in case of RF pulse? So we know that Hamiltonian will be given by minus mu dot bt, And what are the active magnetic fields which are present during an RF pulse? So then it will be Hz, that is the Zeeman part of the Hamiltonian, and the RF part, that is the pulse part of the Hamiltonian, right? So this is coming because of B1 field, and this is coming because of B0 field. Both the fields are present, right? Okay, so that's how there are two components to this minus B naught minus mu naught BT. So B0 and B1. Okay, so let us see how do we write the Hamiltonian. So if we remember our block equation, block description, there we had actually written BRF as B1 cos omega RF t plus phi I cap, because this was along, let's say, x direction, plus we had sine omega RF t plus phi j cap, right? This was the BRF field form. So very similar form will be written for Hamiltonian here. So Hamiltonian will have omega Iz. I'll come to that why it is omega I, plus omega 1 Ix cos omega RF t plus phi plus Iy sine omega RF t plus phi. So if you remember that B1 field is applied as the magnitude of B1 field is actually 2B1, which is linearly oscillating field, which is then converted into or assumed into clockwise rotating and anti-clockwise rotating component, and one of the components will be the resonant component, other will be the non-resonant component, and here we have considered one component here. So that's how it is omega 1 and not 2 omega 1, because it's coming from half of the field actually goes towards resonant component. So that's why this is it. And omega I here considers so omega I is equal to omega naught 1 minus sigma part, so and sigma of I spin. So that's how it contains the chemical shift information of I spin. So that's why instead of writing omega naught, I'm writing it as omega I. Okay, so this will be the Hamiltonian, where we can clear during an RF pulse, so where we can clearly see that there is a time dependent coming into picture, right? So this is time dependent. Now our goal is to find a unitary operator, and by applying a unitary operation onto the density matrix, we want to remove this time dependence part, right? So what will be the choice for the operator U that renders H as time independent? Okay, so since in rotating frame we precess about the z axis with omega RF, the choice of U can be written as exponential, this will be I omega RF t and then Iz. Okay, so that will be our unitary operator U, which when applied onto the density operator, it renders Hamiltonian as time independent. So let us see how it is done. So then what will be the H prime? H prime will be nothing but exponential I omega RF t Iz H exponential minus I omega RF t I z plus the other part, which is plus, this will be minus I u du inverse by dt. And what is u? U is this. So instead of this, now I will write exponential I omega RF tiz d exponential minus I omega RF t iz divided by dt, right? Okay, now what are the different parts of h? H will have, as we have learned, this will have omega I iz. Second part is omega 1 ix part cos of omega RF t plus phi, and the third part is omega 1 iy sine omega RF t plus phi, right? And of course this last part will be this term. So let us first calculate this portion over here, which is easy to calculate, and so that we can calculate the complete h prime. Okay, so let's see what happens to minus I u du inverse by dt when u is given as this form. Okay, so this is minus I e I omega RF t iz d e minus I, this will be plus I, right? This will be plus here. No, sorry, this will be u inverse, so that is correct. Actually, this will be negative. So if I take inverse of this, this becomes negative, so that's how the negative sign is there. Iz divided by dt. Now what I get, if I take time differential of this, I have minus e I omega RF t iz, and other than t, basically everything else comes out. So that means I have minus I omega RF iz, and I have e minus I omega RF t iz. So this is inverse, so it gets cancelled. So that means I'm left with, and then it is minus into minus plus, and then I have I square, which is negative. So minus omega RF iz, right? Okay, so this portion gives me minus omega RF iz, which will go here. Okay, now let us apply this transformation onto first part, which is omega I iz. So if you notice that if I'm applying, so this is h prime, let's say I'll call it first part, So if I'm applying BCH formula onto this, you will see that all the commutators will be IZ type terms, right? IZ. So because it's the same operator, so IZ commutes with IZ, that means all such terms will go to 0. So that means you're left with only the first part, which is nothing but the same, omega I IZ, right? So this is also understandable because there is no time dependence to it. So if we are trying to apply a transformation using the unitary matrix or unitary operator, it should not change the Hamiltonian, right? And it is not changing. So that is understandable. So BCH formula will contain all those terms will go to 0, and then you're left with only omega IZ. So explicit calculation you can try, and if there is any problem we can of course discuss. Okay, now let us calculate H prime on the second part. What is the second part? Second part was Ix cos omega RT plus phi. Okay, so the operator part is Ix, rest is just the frequency in the phase. Okay, so let's try E I omega RF T I Z into omega 1 Ix cos omega RF T plus phi E minus omega RF T IZ. So now if you apply BCH formula onto this, what do I get? So let me go to the top. So if I write the BCH formula again, so sigma T is equal to E minus IHT sigma 0 E plus IHT. So in this case, in the current case, the H is equal to minus omega RF, right? I mean, if you see here, rest is nothing but I and T, so your H is omega RF IZ, and sigma 0 part is nothing but omega 1 Ix cos omega RF T plus phi. Okay, so now if I'm applying BCH formula to the second part, what I get is sigma 0. So sigma 0 is omega 1, or let me just keep this out for now because this will be applied everywhere. So what I'll do is I'll just instead of sigma 0, I'll just keep Ix over here, and rest will be multiplied later. So I'll just treat it as Ix, and then minus IT by 1 factorial and minus omega RF IZ and commutator between Ix, then IT square by 2 factorial minus omega RF IZ minus omega RF IZ, double commutator now Ix, and so on, right? So here what I will do is I will take minus omega RF also out, so this will simplify Ix. So if I take minus omega RF out, I will be left with minus omega rf t by 1 factorial iz ix plus so here 2 times minus omega rf, so this will be square, so minus I omega rf t square divided by 2 factorial, and I'm left with iz ix double commutator. Similarly, third term will be minus I omega rf t whole cube divided by 3 factorial, and I will be left with iz ix and so on. Okay, now let's see what is the relation here between the spin angular momentum operators. So if you remember, we had discussed this ix iy, it's a cyclic commutation which gives you iz. If I take iy iz, it gives me ix. If I take iz ix, it gives me iy. So that means if I'm trying to calculate for iz ix, I will get iy. And now if I'm calculating this, so iz double commutator, so iz ix I already know, which is iy. So this will be equal to I will come out from here, and I will also have now I will have iz iy commutator. So iz iy is negative of this, so I will have minus I ix, right? So that means this will be I square will be negative 1 into negative will be positive, so you will have ix term. Okay, now if this is ix, that means this whole thing will be ix only, so the third term will be iz ix, which is nothing but the first term, right? iy. If third term is this, then my fourth term will again be ix. That means, sorry, I am alternating between iy and ix. So the single commutator is iiy, double commutator is ix, triple commutator is iiy, fourth commutator is ix again, and it will keep on going. So I can write this whole thing again as ix minus I omega rf t by 1 factorial into iy plus minus I omega rf t square by 2 factorial into ix minus I omega rf t cube 3 factorial. This whole thing will be again iy and so on, right? Now if I simplify this, and I will get ix, this will be equal to minus into minus plus, and then I square will be negative, this is I here, so this is minus omega rf t divided by 1 factorial iy, and this one over here, this is minus square will go positive, I square will become negative, so I'm left with minus here omega rf t square divided by 2 factorial ix. What I'm left with here is negative cube will be negative, so negative, negative, positive, and I cube will be negative I into I will be I square, negative I square, which is plus 1. So this will be plus omega RF t cube divided by 3 factorial IY, and so on. Right? So if I separate out the components for IX, I'm left with 1 minus omega RF t square by 2 factorial, then this will be plus omega RF t 4 by 4 factorial, negative, and so on. And then similarly, if I am taking out for y, I can take minus iy out, so I will be left with omega RF t divided by 1 factorial minus omega RF t cube divided by 3 factorial, and so on. Right? So if you notice that this is nothing but cosine series and sine series, right? So this is Ix cos omega RF t minus Iy sine omega RF. Right? So this was on the second part. Now let's say what is the third part over here. Third part was the Iy term. Okay. So H prime, third part was Iy term, and I insist you to do this calculation, and what we will get there is Iy cos omega RF t, let's not have this, plus Ix sine omega RF t, right? And of course this whole thing will be multiplied with omega 1 sine omega RF t plus v. Similarly, the second portion will also be multiplied by with this. So now the total transformed Hamiltonian can be now written as omega I Iz. The minus u du prime part will be minus omega RF Iz. Okay, and the rest of the two parts are now plus omega 1 cosine omega RF t plus v. The Ix part, which was cos omega RF t minus Iy sine omega RF t. Okay. And finally the third part, which is omega 1 sine omega RF t plus v Iy cos omega RF t. This will be plus Ix sine omega RF t. Right. Okay. So now if you notice that this is omega I minus omega RF, which is nothing but the offset, very similar to the rotating frame transformation, and then this is Iz plus omega 1 times, So if I take this inside and separate the variables for ix, what I'm left with is ix into cos. So this will be cos A cos B plus sin A sin B, right? So that will be cos A minus B. So this implies that this will have omega RF t plus phi. This portion is A, and then I have omega RF t. This portion is B. So cos A minus B, and for IY this will be omega 1 IY sin A minus B, right? Because now this is for IY the components are sin A cos B minus cos A sin B, right? There is a negative sign over here, so that will become omega RF t plus 5 minus omega RF t, right? So now this is A, this is B. This is offset IZ plus omega 1 IX cos phi. So now this thing nicely cancels, so you're left with only cos phi plus omega 1 IY sin phi, right? So H prime has now nicely get rid of the time dependence, right? So no time dependence here. At least in the RF part, right? Okay, so now once the Hamiltonian is shown to be time independent, that means now you can apply the solution to the Liouville-von Neumann equation and find out what is the value of sigma t at any given time, right? So basically you can find out the time evolution of density operator, even though the original Hamiltonian was time dependent, but after going into rotating frame by doing the similarity transformation, you have gone into you have converted the Hamiltonian into a time independent part, and then you can apply the similar solution to find out the density matrix evolution, right? Okay, that is all for today. In the next class we will try to see further applications of density matrix. Thank you.